Hello, so this is video number 2 of section 6.3. So as promised, we're going to start off with an example of basically what we talked about last video. So we proved the orthogonal decomposition theorem, which again states that if given a vector y and some subspace W spanned by any number of vectors, we can find the in a sense, the closest vector to y in W, called y hat, which is also known as the orthogonal projection of y onto W. And so that's what we want to do here. So we're given this subspace W spanned by vectors u1 and u2, and we want to find the orthogonal projection of y onto W, which again is usually denoted projection of y onto W. And just for the moment, in the orthogonal decomposition theorem, this is the vector y hat. So this vector, which we're about to define, is the closest vector contained in W to y. And after doing this example, we will actually prove that statement which I just made, which says that this projection of y into W or onto W is in fact the closest vector in W to y. So by the theorem, this is equal to y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2. So we basically do this projection of y onto each vector and then take the sum of these two vectors. So remember that these fractions represent a dot product over a dot product, which in this case means that, again, these fractions are themselves just scalars. So the numerator of the first fraction, notice, is y dot u1, so negative 1 times 1 plus 4 times 1 plus 3 times 0, over u1 dot u1, which is just all of the entries the sum of the squares of the entries of u1, times the vector u1, plus now y dot u2, which is negative 1 times negative 1, plus 4 times 1 plus 3 times 0, all over u2 dot u2, which is negative 1 squared plus 1 squared plus 0 squared times the vector u2. And so it's a lot, but I mean it's just, this theorem is so powerful and so cool that I personally don't mind doing a few dot products. So working through all of the dot product, you should get 3 over 2 times the vector u1 plus 5 over 2 times the vector u2. And so now we can just sum the vectors across. So this would be 3 over 2 minus 5 over 2, which is equal to negative 1. And 3 over 2 plus 5 over 2 is 8 over 2, which is equal to 4, and then 0. And so then this is the projection of W onto Y. Y onto W. So the projection of Y onto W. Sorry, I always get the order wrong because it's put in the opposite order of the way you say it. So a couple things that I want to check about this example before moving on. So if we've claimed that this is in fact the projection of y into W, well, remember that the orthogonal decompositions theorem says that if we let z, and so again I'll kind of put a note here that this is the vector y hat, that if we let z be the vector y minus y hat, then z should be in W perp. And so this actually is sort of the way you can check, did I do this work correctly? What you should always do after calculating a projection like this, especially because there's so much arithmetic, is quickly do this subtraction and verify that the vector z you get, which in this case is the vector 0, 0, 3, is in fact orthogonal to both u1 and u2. Thankfully, in this example, it's not terribly hard to see, because notice here, this vector z has zeros in its first two coordinates and a 3 in its third coordinate, and u1 and u2 both have zeros in their third coordinates. So z is in fact in W perp, meaning it's highly likely that we calculated this vector correctly. In fact, actually guaranteed, because remember the orthogonal decomposition theorem says that this decomposition of y equaling y hat plus z should be unique. So we're going to return to this example in a second, but first I want to prove what your book calls the best approximation theorem, where we're actually now going to show, in fact, that the length of this vector z is the smallest distance from y to this subspace W. And we're going to prove this in general, not just for this example. So if you're following along on the worksheet, there is something before that. I think I will return to that in a second. I might actually, as I'm saying this, if I haven't updated the worksheet, I will return to the small little paragraph before Theorem 9 after this. If I have updated the worksheet, then ignore what I'm saying. Actually, I probably will have to update the worksheet because to make sure that I have everything updated to account for where the videos are actually at. Originally, actually, this example I had planned for video 1, but given the length of video 1, I decided to move it. So anyways, so this is called the best approximation theorem, and this will prove the claim that I've been making about the vector z. So let W be a subspace in Rn. And we're going to let y be any vector in Rn. So y might be in W, it might not be. We don't really care. We're going to let y hat be the orthogonal projection of y onto W. Then y hat is the closest vector in W to y, in the sense that the distance from y to y hat is always smaller than the distance from y to any other vector. So it is the closest vector y hat, that is the closest vector to y among all of the vectors in W, because if I take any other vector in W, and here we're just going to let v be this sort of stand-in for any other vector in W, the distance from y to y hat is strictly less than the distance from y to v. So why is this? So I'll quickly talk about the proof, and again, with most of the proofs now, there's an outline in the notes that I would highly encourage you to look at. So notice that by assumption, y minus y hat is orthogonal to every vector in W, meaning is that it is in W perp. And so this means, so this is the vector, sorry, I'm looking at the proof. This is the vector z in the orthogonal decomposition theorem. So we're going to sort of do this trick in math that mathematicians love to do. And we're going to express the value of y minus v as the difference of y minus y hat and the sum of y hat minus v. So what I've done here, so keep this in mind, the value of y minus v, notice all I've done to the right side of this equation is simultaneously add and subtract y hat. So I can do this again because this is equivalent to adding 0. And I like to say in math, we're just sort of adding 0 in a clever way. So in doing this, because of this note, well, first observe that y hat minus v, this vector, y hat minus v, is contained in W. So these two vectors, y minus y hat and y hat minus v, are orthogonal. So now we can call on, of all things, the Pythagorean theorem. And what this implies is that the squared length of y minus v is equal to the sum of these squared lengths of these two vectors. And again, that's because these two vectors are, in fact, orthogonal. But this actually just proves the theorem outright. Why is that? Well, what are we trying to show? We're trying to show that the value of this vector, which we have here, so maybe I'll call this 1, and the value of this vector, which I'll call 2, which we have right here, well, we're trying to show that 1 is less than 2. Notice that y hat and v specifically were assumed not to be equal. And so I actually should point out here, I'll make that assumption now. We're assuming that v and y hat are not equal, right? We're assuming that v is any other vector in W, which means this is positive, right? But what do I have here? I have positive number plus definitely positive number, or actually non-negative number. This technically could be 0, which we'll see in a second. Non-negative number plus definitely positive number is equal to another number. But since this number is definitely positive, that means that 1 has to be less than 2, because we're adding a definitely positive number to get from 1 to 2. And so, in fact, y hat is in fact the unique closest vector in W to y. So, with this theorem in hand, we can now return to our example and definitively calculate the minimum distance from y to the subspace W in our original example. So I'll rewrite this on the board. y is the vector -1, 4, 3. W is the subspace spanned by U1 and U2. And since I defined U1 and U2 well, they're actually, it's not too long. U1 is the vector 1, 1, 0. Let me double check to make sure, yes. And U2 is the vector -1, 1, 0. So recall that the projection of y onto W was the vector -1, 4, 0. And the difference of y minus this projection was equal to 0, 0, 3. And so what, and we'll call this vector z. And so what the best approximation theorem was claiming was that the distance from y, and actually I should say shortest distance from y to W is equal to the length of z, which is 0 squared plus 0 squared plus 3 squared, which is just 3. And so this is one of the few examples where I might have been able to tell you this. And so I think this actually example gives a nice intuitive idea about exactly what's going on. So I probably could have told you that the minimum distance or the shortest distance from y to W is equal to 3, because notice y as a vector has a non-zero term in its third entry, 3, right? U2 and U1 each have 0 terms in their third entries, but U1 and U2 are linearly independent. So in a sense, this non-zero third entry was the only thing keeping y from being in W. And so this distance of 3 makes sense, right? Because all we would have to do is just turn that 3 into a 0, projection of y onto W, in order to find the closest vector in W to y. All right, so I think that actually is a good place to wrap up this video. So video 3, we will just go over a few more properties of orthogonal projections, and then we will wrap up the section.